In the northern hemisphere of the planet Uranus, something very strange is going on. In 1986, the Voyager 2 probe flew through the region and found nothing but bland, unchanging clouds. But when we looked back at that same region with powerful telescopes decades later, we saw gigantic storms brewing there. What's behind this mystery? Did these storms always exist but were just invisible? Or are Uranian storms only visible once every few decades? And what exactly causes them to appear and disappear? That's what we'll talk about today. This is our channel. When Voyager 2 visited the outer solar system in the 1980s, it was equipped with a camera and a spectrometer. The camera took pictures of Uranus in the visible wavelength range, while the spectrometer analyzed how well different wavelengths of light got through Uranus's atmosphere. Both instruments were essential to understanding what the planet is like. When we look at images of the visible light from Uranus, we can see that it has rings and clouds. The rings are intermediate in complexity. They re-intermediate between the more extensive set around Saturn and the simpler rings found around Jupiter and Neptune. Uranus's clouds, however, appear to be quite simple. The images show a jumbled mass of clouds with no discernible structure. There don't seem to be any continents, no oceans, no recognizable shapes or features. Voyager 2 took images over a time span of only about 6 days, however. So if there are structures there, they may have been missed simply because the planet was photographed at a bad time. The spectrometer measured how well light made it through Uranus' atmosphere and so told us something about its chemical composition. It revealed that Uranus's atmosphere consists mostly of hydrogen and helium, much like Jupiter and Saturn. And since Uranus doesn't have an active magnetic field, these gases must be in liquid form deep inside the planet. The spectrometer also found methane in Uranus's atmosphere. Methane absorbs red light and reflects blue and green, giving Uranus its beautiful iconic color. It also found ammonia ice clouds floating above the planet's surface. The ammonia forms ice crystals which reflect light and make Uranus visible from Earth. Finally, the spectrometer found some water vapor in Uranus's atmosphere. The abundance of gases, liquids, and solids indicated that Uranus had a deep atmosphere with many layers, and each layer might behave differently. Unfortunately, though, the data from the spectrometer didn't reveal any winds or storms. But even if there were storms on Uranus, they wouldn't necessarily be visible in the wavelength range that the camera could see. Storms typically appear dark against the brighter background of their surroundings. But since Voyager 2 also found no other features on Uranus's surface, we couldn't tell whether or not there were any storms. For decades after Voyager 2's visit, scientists assumed that Uranus was a boring, calm planet. But then in the early 2000s, ground-based telescopes started to reveal the truth. Using advanced techniques, they were able to peer through Uranus's thick atmosphere and see that there was indeed something going on beneath the placid surface. In 2004, a team of astronomers led by John H. Rogers of the University of Virginia used the Hubble Space Telescope to measure variations in the brightness of Uranus's light. These brightness variations indicated that there were clouds on Uranus that were higher and darker than their surroundings. This suggested that underneath the featureless clouds, there were rising thermals similar to those seen on Jupiter and Saturn. In 2014, another team of astronomers used the Very Large Array, a radio telescope in New Mexico, to map variations in the radio waves coming from Uranus. They found bright spots indicating the presence of storms. And in 2015, the two teams that made the previous discoveries joined forces to carry out a long-term monitoring campaign. They monitored Uranus for 13 months with both optical wavelengths and radio waves. Their results surprised them. They found 9 new storms, bringing the total number of known storms to 10. The new storms were intermediate in complexity, midway between the simpler storms on Jupiter and Neptune and the more complex ones on Saturn. 6 of the storms were opaque and appeared dark against the background of Uranus's clouds. 3 of them were transparent and stood out as bright spots. And intriguingly, all of them seemed to occur in the northern hemisphere. But the most surprising part of the discovery wasn't the storms themselves, it was their size. Some of the storms were huge, spanning hundreds or even thousands of kilometers. They were so big that they would fit the entire United States several times over. At the time, researchers said that the storms were so large that they were probably an integral part of Uranus' atmosphere. But how did these storms come into being? It's not entirely clear, but the leading hypothesis among astronomers is that the storms are driven by changes in temperature with depth. If the atmosphere has layers in which different gases and liquids condense at different depths, then heat released during condensation could fuel convection currents in the atmosphere, leading to rising thermals and eventually storms. The fact that the storms appear to be concentrated in the northern hemisphere suggests that they relinked to Uranus as seasons. Every planet in the solar system experiences seasons as it orbits the Sun, but the seasons on Uranus are particularly extreme. Uranus is tilted on its side relative to the Sun, so each pole experiences decades of continuous daylight followed by decades of continuous darkness. During these decades-long summers, temperatures at the poles can rise as high as 20 degrees Celsius. And during the winter, they can plummet to minus 220 degrees Celsius. Since the storms seem to occur where the temperature changes the most, they might indeed be caused by the changing seasons. However, this raises another question. Why does it take decades for the storms to appear? Why weren't they already there when Voyager flew past in 1986? To understand why, let's think back to the atmosphere of Earth. During Earth's summer in the northern hemisphere, the polar regions receive more sunlight and become warmer than the surrounding regions. As a result, air rises at the poles and sinks at lower latitudes. But since Earth's atmosphere isn't perfectly still, eddies and currents quickly mix everything up. You get localized areas where colder air sinks and warmer air rises, which makes thunderstorms. If Uranus's atmosphere works in a similar way, then it should have storms in its northern hemisphere when it's summer there. But the difference is that Uranus is tilted so far over that the polar regions receive almost no sunlight for 20 years at a time. So the atmosphere can't mix easily. Air can't travel from the equator to the poles, nor can it go sideways from one side of the planet to the other. Even though the temperature differences between the poles and the equator can be enormous, the atmosphere remains stratified. This stratification is also seen in Earth's lower atmosphere, which is why planes fly so high to take advantage of tailwinds during long flights. But just like Earth's atmosphere, Uranus' atmosphere will eventually find a way to mix things up. Eddies and currents will break through the stratification and mix warm air from the equator with cold air from the poles. Eventually, this mixing will produce the storms that we see. We don't know exactly how these eddies and currents work on Uranus, but we have some clues. In 2021, researchers noticed that the speed of Uranus's storms increased significantly when the planet approached the equinox. During the equinox, the entire planet receives equal amounts of sunlight, so the atmosphere is equally warm throughout. This is similar to Earth's spring and fall when the weather is often unsettled and storms are common. This observation suggests that the mixing process is somehow triggered by the equinox, but exactly how remains a mystery. On Earth, the winds blow around the planet in giant circular motions called cyclones and anticyclones. And since Uranus rotates almost exactly on its axis, it's plausible that something similar happens there, too. When the stratification of Uranus's atmosphere becomes too great, strong eddies will emerge to mix things up. Then, when the planet reaches the equinox, these eddies will reach peak strength. But despite all the clues, we still don't know exactly why Uranus needs decades to develop storms. Maybe it takes decades for the atmosphere to build up enough energy to overcome the stratification. Or maybe there's some other mechanism at play that we haven't thought of yet. In any case, it seems likely that these storms are always there, just invisible to us. We can't actually see the atmosphere of Uranus except from the side. From our perspective, Uranus' flat disk hides most of its atmosphere and leaves us with only a glimpse of the top layer. This is why we can't see the entire structure of the storms, but only parts of them. Since the storms are tilted relative to our line of sight, they appear elongated. Also, the orientation of the elongation tells us the direction of the winds within the storms. And since the winds mostly blow parallel to the equator, the storms look elongated parallel to Uranus's equator. So next time you're looking at Uranus through your backyard telescope, remember that although it looks featureless and calm, beneath the surface, giant storms are raging, bigger than anything we've ever seen in our own solar system. Thanks for watching. If you enjoyed this video, please subscribe and check out our other videos on the mysteries of the outer solar system, Neptune's dark spots and rings. Click here to watch that video. All the best and see you next time.